Good morning, afternoon, and evening, everybody, and welcome to today's webinar, Beyond the Heat, Mastering Battery Safety and Thermal Propagation. I'm Ashley Barnes, and I'm delighted to host this critical discussion on behalf of the Automotive Group. It's fantastic to see so many of you joining us today, whether you're from the automotive sector, battery manufacturing, energy storage, or the regulatory field. It's clear that battery safety is a top priority across industries. As we push boundaries in battery technology, safety remains a non-negotiable factor in its development. The risks associated with thermal propagation, thermal runaway, and fire hazards continue to be major challenges, ones that, if not properly addressed, can result in costly recalls, regulatory non-compliance, and even public safety risks. That's exactly why we're here today, and our experts Maria Quant and Franz Evegren from RISE, the Research Institute of Sweden, bring a wealth of knowledge in fire safety, battery testing, and transport safety regulations. They will share the latest research, innovative testing methodologies, and best practices to ensure that battery technologies remain both safe and sustainable now and into the future. So, what to expect today? Well, we will understand thermal propagation, what triggers it, how we can prevent it. We'll look at advanced safety testing, how to ensure compliance within the evolving regulations, and best practices for battery safety, practical strategies for automotive, energy storage, and battery manufacturing. This is an interactive session, so we encourage you to ask questions, share your perspectives, and engage in the discussion. And you're able to do that by dropping your questions into the Q&A section, the Q&A tab that you'll find along the bottom of the window. And I shall be rejoining our speakers at the end of today's webinar to put your questions across. So once again, thank you for being here, and let's get started by please welcoming Maria Quant and Franz Evegren. Over to you guys.
Yes, thank you very much for the introduction. And like Ashley said, I'm a researcher at the RISE Institute of Sweden. And Franz is also working at RISE. And today we will talk about battery safety, thermal propagation, and safety testing. And RISE Institute of Sweden, we are over 3,300 employees, and we are spread around all over Sweden and also in Norway. But me and Franz, we work at the Department of Fire and Safety in Borås, where we have worked with fire testing since the 50s. So we test everything from doors to vehicles. But lately, it's been a lot of focus on testing the batteries. And we have a brand new battery safety lab, which Franz will talk a bit more about later on today. So on the market today, there are many different battery technologies, and they have different working principles, the properties and the safety aspect varies. And batteries can be divided into two different categories, primary and secondary batteries. So it's rechargeable or non-rechargeable. And if you look at the rechargeable batteries, we have older techniques such as lead acid, nickel cadmium, nickel metal hydride, and then of course the lithium ion batteries, which are the dominating technology on the market. And we also have newer technologies such as sodium ion, solid state batteries, and flow batteries. But today the focus will be on lithium ion batteries. And they are a big family of batteries. So they also come in different shapes with different properties and also different safety risks. But one thing that all lithium ion batteries have in common is that they need to be operated under good electrical and environmental conditions. And if we look at this slide here, we see voltage and temperature on the axis. And in the middle, we have two windows, one optimal life window and one safety window. So it illustrates that we need to stay within certain temperature ranges or voltages. Otherwise, we can have safety issues, and we can have accidents related to the batteries. So what happens then if we don't operate under the right conditions, or if any other error happens? The cells will then enter a state called thermal runaway, and it can be triggered by overcharge, over discharge, or external heating, also from deformation or penetration, and also from short circuits, both internal or external short circuits. So what happens then in the cell is that the temperature starts rising, which will trigger chemical reaction, exothermic reactions. So more heat will be produced, which triggers even more chemical reactions until the temperature is uncontrollable, and it rises very quickly, and the event is then very hard to stop. And what happens to the cell? It starts producing gases, so it will swell, and then the gases are vented, or the casing can then rupture or explode, and the gases that are released can catch fire or cause an explosion. And in a battery system, we usually have many cells. So if this happens then in one cell, it's likely that this will propagate, and we can then have a thermal event in the whole battery system. And what exactly happens, the chemical reactions then on cell level, of course, depends on the material, the chemistry, and so on. But here is a figure to illustrate a little bit what happens. And the more the temperature increases, the more material inside the cell starts to degrade, and different gases are being produced. So it's these gases that then are venting or coming out from the cells. And like I already said, we usually have many cells in a battery system. And if it starts thermal runaway in one cell, it's a very high risk that it will spread to the next cell, like a domino effect. And in this figure, we have a plot from an experiment in our lab. And on the axis, we have the heat release rate, which is more or less the energy of the fire. And on the other axis, there is the time scale. And here we can clearly see how the cells are getting more and more involved as the thermal event is allowed to propagate. So first, the trigger starts in one cell, but around 70 to 80 minutes in, almost all cells are involved in the event until they are completely burned out. So this is a real example of how thermal propagation can look like in a lab environment. And the thermal runaway propagation can, of course, cause major fires and explosions. And we can often read in the news about accidents related to battery energy source system or electric vehicles that catches fire. But here I just want to highlight one accident that was in China in 2021. And in this facility, they had placed the battery energy storage system outside the building, and they had LFP cells. And one cell entered thermal runaway, and it propagates. So in the end, over 100,000 cells are involved. And there is a fire and explosion in the energy storage building. But what also happens is that gases that are being produced are also transported in an underground cable trench to the main building. And there is also an explosion in the main building. And in this case, firefighters and personnel lost their life. So it was a very tragic accident. And the link to the paper where they analyzed it is presented here if you're interested in knowing more. But the point is this propagation can then cause very severe incidents. And then why do these incidents occur? And first of all, statistic in this field is lacking because in many cases it's really hard to see the root cause. If you come to an incident, it's hard to see what really happens. And also these accidents are quite new since batteries are also quite new to the market compared to other energy storage systems. But the EPRI have collected some data, as I have presented in this figure here, where they have looked at failure by root cause and also failure by element. And if we should draw some conclusions, we can see that incidents can occur at any stage, but are most likely during integration, assembly, or construction. And if we look at the graph to the right, we can see that batteries and modules only represent 11% of the failure by elements. So they are not the major cause for these incidents. So it's in other parts of the system, such as the controls or balance of the system, that usually start the incidents, so to say. And UL have also looked at failure types in residential energy storage system. And in 6.7% of the cases, gas is vented, but there was no fire or explosion. And in 75% of the cases, there was a fire related to the incident. And in around 18%, there was an explosion. So explosions are common, and the risks of explosions can, of course, not be ignored when we speak about battery safety. And right now, and me and my colleagues at RISE, we have a project called COMBAT, or Compartment Explosion Induced by Batteries, where we study the explosion risks related to lithium-ion batteries in enclosed spaces. And it's ongoing, but the results will be published both at the webpage and also at our LinkedIn page, Batteries at RISE. So if you're interested in batteries and explosions risk, I really recommend you to look at this project and the results when they are up. Yes, and before I hand over to Franz, I just also want to discuss a little bit what parameters that can affect the hazards. And of course, it depends on what level we are talking about. And we have cell level and system level parameters. And if we look at cell level, we know that the state of charge, the chemistry, the trigger method, cell history, and also cell manufacturer will influence the effect of the hazard. And on system level, it's the safety systems such as thermal management system, safety vault, thermal barriers, battery management system, current interruption devices, fuses, and so on. And also the design, where have we placed the cells, what distance do we have between the cells, and also placement of other electrical components, and then safety systems such as ventilation, detection system, and suppression systems. But if we go a little bit more into cell level, one thing that affects the outcome is the state of charge. And a higher charge level means a greater amount of electrical energy is being stored. So we have more potential energy, which usually leads to more than violent thermal runaway reactions. And here I have two figures also from our fire labs, where we looked at modules of NMC cells, and everything was the same capacity, same, except the state of charge. And here we can clearly see that the higher the state of charge, the more violent the event turned out. And to summarize a little bit on what state of charge have an effect on, then it's the total gas production rate, also the total gas production, the composition of the gases that are released, and the mass loss, and also thermal runaway onset temperatures. So it has a great effect on the event. And then, of course, we have the battery chemistry. And when we speak about battery chemistry, it's usually the cathode material that we refer to. And as a researcher within the field, I get the question a lot, which is the safest chemistry? Is LFP safer than NMC and so on? And I also see a lot of these type of tables where it says safety, high, medium, low, low, medium. And what do we really mean when we talk about safety? And to illustrate that, I have an example from a scientific paper where they have studied temperatures and compared LFP, LMO, and NMC cells. And in this paper, they looked at onset temperature for self-heating generation, temperatures at which battery safety valves opens, and the temperature where the separator collapse, and also the maximum temperature in the experiment. And here are the results from that study. And if we look at the onset temperatures, we can see that they are higher for the LFP cell, and it's around 130 in this case, versus it's around 90 for the LMO and NMC cells. But if we go to the third column and see the temperature where the separator is collapsing, it's actually lower for the LFP cell than for the NMC cell. And usually when the separator collapse is where we get the internal short circuit. And that's usually where this violent thermal runaway starts. So it's important to know what we are talking about when we speak about safety. And so, like I just said, LFP cells then have higher thermal stability than NMC cells. But the literature have also shown that the gases contains generally more hydrogen gas and hydrocarbons, which can result in a lower flammability level, which instead can increase the explosion risks. So keep in mind when you speak about safety, what do you mean? Thermal stability, gas production, explosion risks, fire risks, and so on. And of course, there are many strategies to avoid incidents, and they can also be divided into different levels. And if we go to cell level, it's mostly the material that is affecting the safety. And there are a lot of research and also batteries coming now with, for example, solid electrolytes or semi-solid electrolytes. And the design is important. Where can these gases vent? And the module and pack level, we then have the BMS, TMS system, and also thermal barriers to prevent thermal runaway to propagate if it has started in one cell. And then safety valves, CIDs, and fuses, and so on. And on system level, the design is very important for safety reasons. And we can monitor and detect the thermal runaway in an early stage by looking at temperature or gas detection, also electrical parameters. And ventilation can be a good way to avoid explosion or through active ventilation or deflagration panels. And then there's also methods for suppressing fires. And there are both water-based system and inert gases system. But since lithium-ion batteries are used in a very large variety of different applications, it is impossible to find one system that fits all. And therefore, it's very important that you test your system. And with that, I will hand over to Franz, but I will also just keep encouraging you to ask a lot of questions in the chat, and we will take care of that after the presentation. But thank you.
Yes, thank you very much, Maria. I hope you can see me and hear me fine.
Yes.
Okay, perfect. So yeah, like Maria said, it's very important to test your system and your safety features. And just a couple of slides about our new battery safety lab, as you can see here in the image, and behind here in the valley is our old fire lab. So this battery safety lab is something that we built because we need it. we have moved the walls in our old fire lab, and here we have heavily reinforced walls, 50 to 70 centimeters. And each door is, it's not a garage door, it's a 100,000 euro steel door, and that is movable, of course. And it's built with these safety features in mind, so we can handle a quite large explosion. And we also are very proud of our flue gas evacuation and cleaning system, as well as the cleaning of our extinguishing water. So we have our own treatment plant, and we clean up to 99% of the exhaust fumes. So we're very proud of that, and we believe that this will be the new standard in the future. But of course, safety is more than the test itself. You need to be able to handle and store large quantities of batteries and perhaps prototypes. And after you test, you need to make sure that they're safely handled, or you can manage thermal runaway if something happens afterwards. You need to be able to charge and prepare it. So in our lab, we have a possibility to cycle batteries in connection to all the labs, but this cycling equipment is separated from the actual lab. So it's on a different floor behind this 50 or 70 centimeter concrete wall. And it's very important that you take care of safety in this whole circle. Disposal and cleaning, of course, is very important. There are many toxins that you don't want to expose your personnel to. And here's just a final image of our lab. Me and Maria, we work mostly in research projects connected to the abuse halls, as we call it. This here, big image down to the left, it's heart of this building. It's the main abuse hall, and then we have 3 small ones, which you can see in these small images on the right, where we can conduct testing on cells and modules. And in the big abuse hall, we conduct tests on battery packs and full vehicles, for example. I will just share a few results from some of the research projects that we have conducted in the past 5-10 years. Much is happening, of course, and we have a few projects running, like Maria mentioned, for example, the combat project looking at explosion risks. But I'll share some of the highlights from the past years. Also, it's not only from the research projects, but also, of course, from doing a lot of standardized testing, for example, according to the UL 9540A, where we conduct tests for cells, modules, and units, and we're going to be certified for installation pretty soon here as well. Something that you maybe didn't know, that the trigger method actually affects quite a lot. Maria mentioned about the SOC and the state of charge, how that can affect the fire development or the development of the thermal runaway. But actually, the trigger method can have an effect as well. There are different trigger methods. You can have a heating ramp. You can have a local heater. You can also expose it to an external fire. You can expose it to a nail penetration or overcharge like this. And what you can see is that the trigger method definitely affects the time to thermal runaway onset. It affects the maximum temperature. It affects the gas production rate and also the mass loss. So in this graph up here on the right, you can, for example, see how we expose the same battery to nail penetration and to a heating ramp, which perhaps obviously affects the development of the thermal runaway in a major way. It was a delay of 13 minutes or 12 minutes about until we achieved about the same thermal runaway in this cell. So in addition to the state of charge, which Maria showed before, the trigger method is very important for the gas production rate, for the mass loss rate, and for the thermal runaway onset temperature. And this is also summarized in this scientific paper published by Ola, our colleague, and several others. I also thought I would mention a few things about battery electric vehicles. We get that question a lot, if they're safer or less safe than internal combustion engine vehicles. And in this project, which we refer to as the ASEA study, because ASEA, they funded the project. Just a second. And ASEA is the European Automobile Manufacturers Association. And we conducted this in 2022, so it's already a couple years old. But the statistics we found show that if you look up to the left, for example, it shows that battery electric vehicles burn not at all as often as internal combustion engine vehicles. If you look at the number of fires in vehicles in America, it's about 1 in 60 that occurs in every battery electric vehicle. So a 60th as common, you can say. If you look at the million miles traveled, which Tesla, for example, likes to compare, it's about a 10th of as common as an internal combustion engine vehicle. And if we also look at Norway and Sweden, Norway is one of the countries with the most electric vehicles, the most electric vehicles in the world per capita. And there we see a factor 8 in difference between internal combustion engine vehicles and battery electric vehicles. And in Sweden, about a factor 10. So it's around there, perhaps not factor 60, perhaps not a factor 2, probably around a factor 10. That's how we summarize these statistics. Previously, I mentioned about how trigger methods and state of charge affects the development. But if you look at a battery electric vehicle, how is the difference then? Well, we have looked at this, and if you want to draw some general conclusions, you can see that the traction or the battery or the petrol actually doesn't correspond to much more than a third or a fourth of the total energy in the vehicle. So it is for that reason natural to see the results that we saw from full-scale testing, namely that the fire growth rate, how quickly it grows, it's not faster for a battery electric vehicle, and the peak heat release rate, meaning the maximum energy of the fire, the peak here, like Maria mentioned, HRR, heat release rate, that is a very common term to measure the size of the fire in fire safety engineering. And it's not larger for battery electric vehicles either, and nor is the total energy released. So, and that follows, of course, from this conclusion or this comparison here at the bottom left, where actually fully charged battery does not contain more than maybe about twice as much energy, but it's relatively in total for the whole vehicle, it's about the same. And more importantly, modern vehicles in the past decades have so much more plastics and have grown also in size in many countries. And that is a far more contributing factors to the size of the fires, actually. You can read more in these reports, of course. Next question that has been asked a lot from society to us as a research institute is, well, can the fixed fire extinguishing system control a battery electric vehicle? And our conclusion is yes. We have seen from series of tests that sprinkler systems in, for example, a garage or on a vessel, on a ship transporting vehicles, that a properly designed sprinkler system can effectively control a battery electric vehicle. But it is important that you continue to have the system activated. Otherwise, what you see here in the bottom left picture will occur, and the fire will reignite or continue to grow again. So it's very important, especially considering the reignition risk. Very important to keep the system activated if possible. We looked at a few different extinguishing systems. Drencher is a term used for sprinkler system when you have it's a deluge system section. On ships, for example, and hangars and tunnels, you can use high expansion foam, and carbon dioxide is also a system that has been used. We haven't conducted tests on high expansion foam yet, but a company in Japan called Kashiwa Tech have conducted some research on this and show that it is possible, but the capacity remains, to me at least, still an open question. The tests were conducted with quite a small Nissan Leaf, so quite a small battery vehicle. Now we see trucks, for example, using up to 1,000 kilowatt hours, so 10 Teslas. A thermal runaway in such a large battery, it really requires that you're able to have a capacity of your extinguishing system for a long time. Carbon dioxide is also a system that we're looking into right now in a project called COFFEE, carbon dioxide fixed fire extinguishing of batteries. So we'll see what comes out of that. But of course, any system will handle the open flames. The open flames will be suppressed by a sprinkler system. They will be extinguished by a carbon dioxide system and a high expansion foam system. But you will probably not extinguish or stop the thermal runaway, and that becomes quite important. There's a statement that BEV fires cannot be extinguished, so it can be. It should be said with some modification, I think. There is also a statement saying that thermal runaway in a vehicle should be extinguished with a massive amount of water. So like I said, you can probably extinguish the open flames, but you will not be able to stop the thermal runaway inside the battery. It requires cooling inside the battery, and it's very ineffective from the outside, and this is the only possibility that we have. Propagation to undamaged cells can be hindered or slowed down if sufficient cooling is provided, but it is very difficult with the current designs. I know that some fire and rescue services are looking into, and some research is looking into using, for example, these fog nails or extinguishing lances. At this stage, our research cannot recommend this, since you might actually damage and cause much more damage than you have already has occurred. In research, absolutely continue to look into it, but for fire and rescue services right now, we cannot recommend it. What is increasingly important instead is to stop the spread of fires between vehicles, since it's very difficult to fully extinguish a thermal runaway. It becomes increasingly important to stop the fire spread between vehicles. We have looked into this in several projects. It started already in 2017-18 in the Brent project, and we looked into it in Brent 2.0 and in the Lashfire project. And what is our conclusion from this research? Well, if you have an active system, a fixed fire extinguishing system, activated without delay, that should be the first resort. Manual firefighting should be executed for life-saving, of course, and as a proactive measure, you can use it, and also to complement the fixed system, or for post-fire control. Well, the main thing you should do is to hinder fire spread. In the Lashfire project, we followed up on an idea to have this, we call it a water lizard, the red thing here you can see on the screen, which works as a fog screen or a water screen. It creates a screen between the vehicles, which can hinder fire spread, and you can install it and then leave it there until you have the situation under control. In this sense, it's also, in this scenario, it's also important to remember that the fire spread to the next battery generally doesn't occur very quickly. Usually we see that we have to expose the traction battery to fire for about 30 minutes of fire exposure before it becomes involved. So you do have some time to conduct firefighting activities. Furthermore, the battery is only a minor part of the fire load, as I mentioned before. So any battery electric vehicle, you're able to avoid fire spread and extinguish the car fire in the coupe of the car, for example, and in all the plastics. So you can still do a lot of manual firefighting. And water, I would like to mention, is a very good coolant for vehicle fires, for any vehicle fire, also a BEV. And water washes out gases from the air as well, reducing the toxicity and risk of explosion. We are looking into the explosion risks in the combat project, like Maria mentioned, and hope to be able to publish some results on that soon. There are also other equipment that is used, not only for firefighting, but not only extinguishing systems, I mean, but also these IR cameras are very useful, so you can monitor the fire suppression and see if the thermal runaway is going again, or if it's cold enough to safely be removed, the vehicle. You can also use these fire blankets, the vehicle fire blankets that have reached a lot of attention in media, I think. or at least in my channels. And they can advantageously be used to hinder fire spread as well. But you shouldn't expect that you stop this or run away with such a tool. Regarding toxicity, this is also something we looked into, both to the ground, so the extinguishing water, as well as to the air. In this project called ETOX, ETOX 1 and ETOX 2. And the general conclusion you can say is that there are several acute toxic gases released from both battery electric vehicles and internal combustion engine vehicles, such as carbon monoxide, hydrogen fluoride, hydrogen chloride, etc. But the main toxin where we see a large difference is HF, so hydrogen fluoride. And it represents the largest difference between electric vehicles and ICEVs. And something special about it is that it has a systemic toxic effect, and that means it can be absorbed through the skin as well. So that it's very gnarly. You don't want to be exposed to it. We have seen that, excuse me, the sprinkler system did have a large effect on washing out the HF. But of course, it also causes a greater mixing of the gases in the space in the enclosure. We have also looked into the firefighting suits in a project called Safe and Suitable Firefighting, and we concluded that state-of-the-art firefighting gear, such as firefighting gear approved according to EN 469 level 2, is a very good state-of-the-art suit that will protect you well also against HF. We also did this investigation in association with onboard firefighting, onboard ships, where you can see that this firefighting gear up in the image on the right here is something used, and that is not a really state-of-the-art firefighting gear that should be used. But EN 469 level 2 is very good. We suggest that it's complemented by a flash hood, a second layer, so an inside layer, and breathing apparatus, of course. And then the firefighters will be well protected from all vehicle fire gases, including those from lithium-ion batteries, such as HF. And then we also have some other recommendations regarding footwear, lightweight cylinders, etc. And you should also remember to not smoke dive for more than about 40 minutes at a time. You shouldn't expose yourself to the heaviest smoke, but these are typical routines for firefighters in general. So just to summarize a little bit, the SOC, as Maria mentioned, and the trigger method will affect the thermal runaway. And the development of, for example, the mass loss. The BEV fires are not more common or more intense than ICVs, but there is a major reignition potential that must be handled. The fixed firefighting systems could be started. It should be started without a delay and will suppress the BEV fire, the flames that is, but you will once again not extinguish or stop the thermal runaway with the system. So therefore, it's important to keep it activated during a manual intervention. A thermal runaway cannot be stopped, like I said. Focus should instead be on controlling the fire and preventing fire spread. Fire effluents are toxic, obviously, both from any vehicle, and should be fought with a suitable firefighting gear, such as EN 469 level 2 suits. The battery explosion risk is something that we are investigating in the combat project, and also we're investigating the use of carbon dioxide for handling battery electric vehicle fires. And that is something that we hope to publish at the end of this year, and then the coffee project end of next year. Just a final note, as you see in my background here, we're doing some advertisement also for the Battery Safety Conference. If you're interested in this subject, I really recommend you to sign up for this conference on the 19th of March. It's in a couple of months. We have a great lineup of speakers, and we're really looking forward to it. Of course, a couple of speakers. Maria will speak from RISE, but we have speakers from Lund University, Daimler, UL, Volvo, and FPA, as you can see here. So it's a full day at JC's in Gothenburg in mid-March here. And if you're further interested, we try to publish all our research on online. So if you don't want to miss any of the news that we have from our research projects, you can always sign up for our news at LinkedIn through this QR code here. And that was it. Thank you very much, and I welcome you back, Ashley.
Thank you so much, Franz. And we shall get straight into the questions. I'll invite... hello, Maria. Right, lots of questions to get through. If we don't manage to get to your question, don't worry, because I have forwarded those across to Franz and Maria, and we can reach back out to you directly after. But let's see how many we can get through. So to begin from Simon, whilst there are no prospective legislations within the UK currently, it's encouraging to see that the UK government have responded to concerns about BESS fire safety. And I believe this is now in the House of Commons for consultation. With regards to international standards, NFPA 855, do you see any international legislation that can be adopted and referred to when designing BESS systems?
Do you want to mention, Maria, something about our best project that we had last year?
I mean, that's some issue with the whole battery energy storage system, that it's like different regulations in different countries and so on. And even within Sweden, we had this issue that everyone was doing different ways in the different cities and so on. So we had at RISE, we did some guidelines. But regarding how this American standard is going to be in the UK, I don't know so much about it, or but I think maybe, I mean, it would of course be very beneficial to have something same type of regulations within Europe and so on. I don't think maybe that was the answer. Maybe Franz, you have something more, or we can.
No, well, I just thought I would mention, I wasn't involved myself, but my colleagues, they conducted a project. It was actually the scope and the main objective of the project was to develop guidelines for the fire safety of battery energy storage systems. So we did develop this based on Swedish conditions. It's applicable from any small battery that you have for a solar system at home to the large sites that our energy providers have with battery energy storage systems. So it's applicable for a large variety of BESS. And I can put the link here in the chat if you're interested to see what we recommend for Swedish applications, you can say. I personally am not fully into all the legislation and prescriptive requirements internationally, so unfortunately I can't give you an answer to that question. But as a basis for that project, we did conduct a literature study where we looked into different standards. I know that they did that.
Yes. And one thing that is quite tricky with this system is especially the explosion risks, because it's very tricky to be prepared for worst case scenario. So for example, if you have ventilation, it can be good to handle maybe a few cells in terminal runaway. But if you have a system where all the cells enter terminal runaway, it's going to be almost impossible. You're going to need big, heavy industry fans in your little garage at home for your Tesla Powerwall. And I mean, that's not going to happen in reality. So it's quite tricky. And also with the larger facilities, I mean, you have to do a risk assessment also based on where are they placed, is it close to water? Because also the extinguishing water is usually very toxic if you use a lot. So you have to see the holistic view of these larger systems safety.
Very good question though. And it's something that is really discussed in many countries in Europe, I think. So international guidelines, I believe, are definitely needed.
Perfect. Friends have actually sent me the link, but I will put that into
Yeah,
into
yeah,
the
I let you put it up for
yeah,
now.
not to worry, but thank you ever so much. So the Camilla asked if you could explain or expand the phrase that you used, the flagration panels.
Oh, so that is like an not active ventilation. So it basically you have some panels maybe on top of the of your container, and when the pressure builds up, they open up to like release the pressure before you have an explosion. But that's also quite tricky with this energy storage system because you need very large. The area where you need to have these panels are very large, and that can give you other issues such as the structure of the building will be weaker. You can have maybe rain coming in. So it's also, you have to have quite a lot to prevent worst case. But we have those in our labs, right? Big ones in case the experiments goes a little bit too wild as a
Yeah, I thought I would
measure. Yes.
share this. I don't know if you can see my screen now, perhaps.
Yeah.
Yes.
Yeah. So unfortunately, I have this chat window. So yeah, so as you can see, these are actually not at the top of these two buildings here in the foreground, and these are actually not solar panels. They are explosion hatches, you can say, or different flagration panels. So we have that in all of our labs here. At the center of the tall building here, it's 20 meters from the floor of the lab to the ceiling or roof that you see here, which also creates a larger volume, which is good. But in case that cannot hold the enclosure cannot hold the pressure, these explosion flaps will open up, and it's the same for the vibration holes, the labs here you can see on the left, and actually for the smaller abuse as well. So it's
Excellent.
an extra safety measure, you can say.
Brilliant. Thank you ever so much. What is the most popular thermal runaway fire mitigation strategy established commercially with lithium-based batteries?
I'm sorry, please, could you repeat that?
So, what do you think is the most popular thermal runaway or fire mitigation strategy that's currently established commercially for lithium-ion based batteries?
So for lithium-ion based batteries, if it's a battery electric vehicle, I think that the most commercially or the most common strategy would be to leave it. If it is in a safe location, for example, in an open space outside in a parking lot, I believe that the fire and rescue services will do everything they can to prevent fire spread, but they will not put focus on much cooling or limiting the thermal runaway inside the actual vehicle. And it depends also when it comes to BESS. I think it depends on what's close by. And I guess that is a common strategy in all firefighting, but since it is very difficult to extinguish, focus is often on hindering fire spread to nearby valuable buildings or things like that. Do you want to contribute anything?
That is also true on cell level. A lot of research and everything is on preventing this thermal runaway to propagate, so you don't get this severe incident.
Thank you. Is there any data? Do you have any data available on how high pressure can get during an explosion related to a certain number of batteries? So I think we're asking for, is there any sort of metric on pressure buildup pertaining to different numbers of batteries?
We will have soon in the combat project, because this is one of the things, one of the team members, Johan Andersson, he is simulating explosions, and we are right now in the stage of collecting as much data as possible so that we can get this type of numbers. So it will be in this study, and right
it
now,
all depends on how much gases are produced,
yes.
at what rate combustible gases are produced. And we, of course, have some experience from conducting a lot of tests with batteries. And from what we have seen, the SOC, sure, it affects how quickly gases are generated. but also other factors. For example, how the cells are stacked and packed inside the module has a major impact on how quickly gases are produced. And that is really what can affect the size of the explosion. So we make some, should you say, justified assumptions and conservative assumptions based on experience in our labs, where we always try to handle this risk of explosion. So we know how to handle each scenario in case it goes south, so to say. But in these labs, I mean, thermal runaway inside a battery electric vehicle is another day of work. So we handle this risk all the time. Yeah.
Brilliant, thank you. And that sounds like a pretty good job around explosion simulator.
Yeah.
Yeah, pretty cool. Do these safety aspects differ a lot with newer technologies such as sodium-ion batteries or solid-state batteries compared to lithium-ion batteries?
I mean, yes, because they also vary within the lithium-ion batteries. But for example, for the solid-state batteries, I mean, the whole aim with those is to have a solid electrolyte. And then if we avoid this flammable electrolyte that we have today, then many of the issues will be solved, and they may not go into thermal runaway, or they will be much more stable. But there are, of course, then other issues with these batteries. It's much harder to get the right connections with the materials, and you usually need high pressure inside the cells and so on. And to the best of my knowledge, there is not yet any fully solid state batteries on the market today, but only semi-solid states. And I think we just started testing those type of batteries within our lab. So they are quite new to the market. And then regarding sodium-ion batteries, we have some projects also, some big European projects and some smaller international projects where we look at sodium-ion batteries. And then of course the material are different than lithium-ion batteries. And one major difference with sodium-ion batteries is that they can be completely discharged. Because with a lithium-ion battery, if you bring it down to 0 voltages, it will be damaged. So if you start using it again, then you have risks. But that cannot happen with sodium-ion batteries. So you can transport it at 0 SOC. And as I showed, the higher SOC, the more energy, the worse the event gets if there's an incident. So that's, and also for sodium-ion batteries, there is a possibility to have aqueous electrolytes, and then they are not flammable. So they will differ. Yes.
Thank you, Maria. It's a bit of a key change, but is the extinguishing water from battery fires more toxic than from other fires? So I guess the question is, do you have any findings on the toxicity of water with, comparing different incidents?
Yes, like Franz presented, we did the ETOX studies where we studied extinguishing water and compared for battery electric vehicles and traditional vehicles. And both water from both situations were toxic, but we could see also because we flashed the battery afterwards, and when we did that, we could see that we had an increase of PFAS, for example, and also like we also said, we usually need a lot of water. So it's important that when you do a risk assessment, if you have a battery and a storage system, you need to have this in mind, that you need to take care of the water. And it was also toxic for living organisms. We did the ecotoxicity test. So yes, but toxic in both cases, but it's also a bit different. We have, of course, metals that are in batteries in the water from the electric vehicles, and we don't have that in the traditional vehicles.
Thank you, Maria. Do you have some insights into how different cell designs and configurations affect the likelihood or the severity of thermal propagation?
I mean, we have seen that depending on the format, if it's a cylindrical pouch or prismatic, the total gas volume can vary which of course then can have an effect on explosion risks and so on. And also, for example, the pouch cells, they are usually made out of softer material, so they can burst or vent much earlier than these with a harder casing, such as prismatic cells. And with prismatic cells, there's usually a valve in the top. And if gases are vented, they usually come out there first. And then you can get more of jet flames if they ignite and so on. So yes, the safety varies. And when you then big a larger system, this is of course important to keep in mind. Where do you want your jet flames to go, or where do you don't want them to go, and so on.
Thank you ever so much. In real world applications, what are the early warning signs of a potential thermal event, and what monitoring technologies are available to detect them?
That's also a very good question, which we are looking into right now. We have a project we call EDOT, Early Detection of Thermal Runaway, because this is something that is really gotten a lot of interest in many different industries. Since it is so difficult to stop a thermal runaway, it would be really beneficial if we could have an early notification or detection of an imminent thermal runaway. I don't know, maybe you know, Maria, if we have any preliminary results from that project?
Not yet, but focus would be gas sensing. And that is, of course, one method to see if thermal runaway has started. But there's also other ways like temperature monitoring. But all these systems have also their own issues. For example, we have done some studies earlier where we looked at gas detection. And then we could detect the gases 15 minutes before thermal runaway. And that's for at least evacuation point of view, that's quite some time. But then we also saw that it matters a lot, the circumstances. If it's in a small confined space, it's quite easy to detect. If it's a large area, it's much trickier. And also sometimes gases are being cooled down and then they go to the floor instead of to the ceiling where detection is usually placed. But I would also say that one thing that we also are very interested in, and I think our colleague Ellen Scott will talk about in an upcoming webinar, is the battery management system. Because it can also give you very early signals. You can see voltage drop or voltage increase. So it's very interesting how the information that we get in the BMS, how can that be translated to useful information, for example, for rescue service, for sending off an alarm, something is about to go wrong, before even we can see temperature rise or gases being released.
That's where I see the largest potential, actually, because there you already have thermocouples built into the battery, and if we can find out a way to communicate with the battery management system, which is acceptable to the OEMs, for example, then I think we would have a much larger possibility to have an early warning. I know in the EDOT project, they're also looking into, for example, acoustic signatures and things like that as well. So they're trying to have a wide perspective, going wide on different technologies, looking into if they can find suitable technologies for early detection.
And also with the temperature measuring, it's also like Franz said, it's measuring on the outside, then it's already started. A lot happened inside already. It's already warm. But there are methods, but more on research days on how to measure directly inside the cells. But to date, they are way too expensive to have in real life applications, but maybe also for the future.
Brilliant. Thank you ever so much. Sorry, I was taking notes as well. Very good. How does battery state of health impact the likelihood of thermal propagation in second life or reused batteries?
Now I'm not an expert in second life battery, but there is an issue because when you get a second life battery, it's like getting a black box. You don't know what happened, how was it used, and so on. So it's a lot of research on how to diagnose this battery. But of course, as the battery gets older, the material age, and some of these degrading mechanisms can lead to safety issues such as lithium plating, and the more lithium plating, the higher risk for internal short circuits and so on. So
I know there have been discussions about a battery passport
yes.
to alleviate the reuse and secondhand use of batteries,
Exactly.
which would present or kind of guarantee the health of the battery. But I haven't looked too much into that.
No, I think it's from the new battery regulation. And I also think maybe Ingvar will talk about that on the next webinar.
Okay, yeah, cool.
We have at RISE expert in all areas. So
very good. We have some questions I've seen on battery passports, so maybe we'll get some time. I'm quite happy to overrun for a little while longer.
Yeah, I think save those questions about the battery passport for Ingvar for the next webinar. Yes. We're not experts in that.
How do passive and active safety measures, such as thermal barriers, shutdown separators, and cooling systems, compare in preventing or slowing propagation? So how do the different safety measures compare against each other, I think is the question.
So like Maria mentioned before, thermal propagation, so spread of thermal runaway from one cell to another cell and from one module to another, is really the key to stop the thermal runaway event inside a battery. So I think most systems for that I've seen are definitely passive systems, but I've seen on a larger scale also combinations with active systems. And of course, when you come to the scale where you want to stop fire spread between vehicles, active systems are very common. So it depends on the scale, but the best is always, of course, every fire starts small, as you know. So the best is always to stop it as early as possible. And there I think that the passive systems are more common. I have seen examples of systems which are active, which, for example, flush the battery with water or with nitrogen, liquid nitrogen. But those are more at a developing stage and nothing I've seen in an actual application. Maria, do you have anything to add on this?
No, I haven't worked so much myself with that, but there's a lot research going on this area where they try different materials for preventing the propagation, such as phase change materials, and so it's a hot topic, so to say. But I haven't worked so much with it myself, so I think we're happy with
that. They cost volume and they cost mass and money, of course. So yeah. It's a little tricky to find an effective, efficient system, and that is also cheap.
Thank you. Interesting question from Bastic. Do the RISE abuse chambers incorporate climatic chambers if the tests are to be carried out in the winter period, since Sweden is a cold temperature region? Do you abuse tests based on IEC standards for your projects, or it depends on what the project defines? Did that make sense?
I will try to answer. Anyways, I will share my screen again, perhaps to support my answer. So if I can just, there we go. So as you see here at the center of this building is the abuse chambers, the large abuse chamber and the small ones. And of course, they're all thermally regulated, so 20 degrees Celsius all year round. Up here, we also have a number of climate chambers, and here we have, you can see an arrow in the right corner, the walk-in climate chamber. It's a large climate chamber. I think it's 2.5 or 3 cubic meters. It can adjust the temperature from -60 to, I think it's plus 150. But with these climate chambers, it's not actually the range that is the tricky part. The tricky part is to change the temperature of a large weight quickly enough. And I think that the capacity of this is 10 degrees per minute for the small ones and 7.5 degrees per minute for the big ones. And the weight can be, I forget. I think it's 1.5 tons or something like that. So that is the tricky part. Yeah, and with the shakers down here to the left, we can conduct vibration testing simultaneously with a climate chamber on top of it. So yeah, we regulate the temperature if we need to in the climate testing, and also in the abuse chambers we have done it, so to say. If we want to increase the temperature or reduce the temperature, we can do that as well. But that is more of an ad hoc experimental studies for our clients rather than the standardized when it comes to combining temperature and causing thermal runaway, which we usually do in the abuse chambers, either by exposing them to fire, nail penetration, or mechanical testing. There we actually want to cause the thermal runaway. For example, to look at how much of heat is generated, or what toxic gases are produced, or how much gases are produced from a cell, from a module, from a whole vehicle, how quick do critical conditions spread to the coupe of a vehicle, things like that. At the moment, there aren't so many standardized standards to conduct tests according to. Most of our testing is done, I would say maybe between 50 and 75% of the abuse testing is experimental at this stage, and the rest is standardized.
Thank you ever so much. How can safety testing be aligned with sustainability goals to minimize environmental impacts while ensuring compliance?
Most, I think, fire labs around the world, or most companies conduct their fire testing either outside or in a facility where they don't clean the gases or the water, the extinguishing water. And as you see up here up in the left corner, this is our smoke cleaning facility, and then we have a combined water cleaning facility together with the fire lab. So these are major investments, and I think that these are the main activities that you can engage in to really ensure sustainable testing, to make sure you don't release toxic fumes to the air and to the water, to the ground. So yeah, and we of course we follow the regulations about how toxic water we can let out to the county's water cleaning treatment system. So we take care of, like I said, to the air we clean up to 90, 99, or usually generally above 95% in all testing of all the smoke, all the particles that we clean away from the smoke before we let it out. So I think this is definitely how you should conduct sustainable testing, and it's only a matter of when this is going to become the standard all throughout the world, I think.
Brilliant. Thank you ever so much. I think what we'll do, we have, well, we've had over 70 questions, so we're never going to get through them all. What I'm going to do is ensure, of course, that the questions are passed directly to Franz and Maria, and I'm absolutely certain that Franz, Maria, and probably some more of the team at Rise can reach back out to you and get into those questions in more detail. Today's webinar will be available on demand, both from the We Automotive Group website, ev-manufacturing.com, and similarly, I'm sure, from Rise, their website, as well as, I imagine, the LinkedIn groups as well. So thank you ever so much for all being here today. A big group. We've had some fantastic questions, lots of fantastic questions, and it's been a really thorough and enjoyable session, Franz and Maria. So thank you both ever so much. This is the first webinar within this particular series with Rise. So we have another 2 coming up very shortly. And again, Franz mentioned Rise's Battery Safety Conference, which is taking place on the 19th of March in Gothenburg, which is certain to be a really unmissable event. So check it out on the website. QR codes there. I'll give you just a second. But otherwise, I will leave Franz and Maria to say their final farewells, and I'll see you all again very soon.
Yeah, thank you. Thank you. Enjoy, and hope to see you at the conference. And like I said, all our research we try to publish. So visit our website or LinkedIn, and you will find out everything we know.
Yes. Thank you very much for listening today.
Much appreciated, everyone. Right, take care. Bye bye for now.
Thank you.
Bye.
Bye-bye.